In this lecture, I'll finish the proof of the existence of partitions of unity. So let's recall what these were, and I'll just state it as a theorem. So I have a compact set in Rn. And an open cover of K. Then the assertion is that then there are continuous functions on Rn, finitely many. So these are continuous functions such that each of them is non-negative, bounded above by 1 for all x in K, and then the support for each I there exists an index alpha such that support of Ci is contained in V alpha. Then the third one, which justifies the terminology partitions of unity, is that Ci I equal to 1 to S, Cix equal to 1 for all x in K. So, and this family of functions C1 Cs is said to be a partition of unity subordinate to the cover U alpha, V alpha. So let's prove that. Let's prove this theorem. For each x in K, since this V alpha family of sets V alpha is an open cover, every x in K is contained in some V alpha. We choose an index which we denote by alpha x with x in V alpha x. There might be, given an x, it might be contained in several of these. We just choose one of them. Next, let us find, so here's the picture. So this is K x, this is V alpha x. Next, I'm going to find open balls. We can find open balls B of x and Wx centered at x with B of the closure of this smaller ball is contained in Wx, which is of course contained in its closure, and that closure should be in V alpha of x. So the picture is this is all right. So in fact, let's make it a bit so it doesn't come near the boundary at all of V alpha. So I'll draw it like this. So this inner ball is B of x and the larger ball is W of x. To be clear, what we can do is we can just take, after all, V alpha x is open. Choose epsilon such that the ball of radius epsilon is contained in V alpha x. Then just take W of x equal to Bx epsilon by 2, B of x to be Bx epsilon by 4. So this is the ball epsilon. Then I take epsilon by 2 and then epsilon by 4. This will ensure that the closures are also contained in as we want them to be. All right, so that's just a minor point. Since K is compact, there exists x1, xs in K such that K is contained in the union of Bx1, Bxs. After all, these smaller balls Bx, as x varies over K, by definition x is inside B of x. So as x varies over K, these small balls will form an open cover of K. Therefore, there are finitely many of them, Bx1, etc. Therefore, and you get these points, x1 up to xs. So we have this. Now the condition that B of x closure is contained in Wx bar, etc. So to be, it's better to have a concrete picture. So let's just take, so what did I do? Yeah, well, actually the sizes of these balls are immaterial because these balls don't make an appearance in the final statement of the theorem. They're just something that we use along the way. So we might, for our purposes, we can take whatever we want. So let's just take this, whatever I had done earlier, epsilon by 2 Bx epsilon by 2, and this is Bx epsilon by 4. Now let's I'll find some continuous functions. We can find S continuous functions such that now this is the epsilon by 2 ball, the larger ball, and this is the smaller one. So what I want, the continuous function should be 1 in the interior of the smaller ball. So if you draw the graph, it will be like this. It will be 1 throughout, and then it will start tapering down to 0 in this annular region. So what with phi I of x equal to 1 for all x in the smaller ball, and outside the larger ball phi I x equal to 0 for all x with norm x, norm, oh actually x is not a, x is not a good thing. X is being used for the center of the ball, so let me call it y. Phi y identically is equal to 0 with whenever outside the larger ball with norm y minus x greater than or equal to epsilon by 2, and everywhere phi y lies between 0 and 1. With y, norm y less than norm y minus x in the annular region is greater than or equal to epsilon by 4. So that's what this picture indicates. So and how does one find such a thing, such a continuous function? This is quite easy. So let's just see what's happening in the case of, for instance, if we are n equals 1. So what I want is, minus epsilon by 4, a ball of radius. Oh, actually, the other thing is that the center is not the origin, but that's not a big problem. So let me just take centered at some point. I have the real line. This is my x, and the ball of radius epsilon by 2 will be just this interval x minus epsilon by 4, x plus epsilon by 4, and the ball of radius epsilon by 2 is the larger interval, this. So what I want is a continuous function. So if I draw the graph of the function, it should be like this. It should be identically 1 all the way up till here. So this is the y-axis. So this is the point 1. And after this, all along this side and all along this side, the function is 0. So the graph is just the x-axis for this part. And I want it to be between 0 and 1 in this transition region, in this interval as well as this interval. Well, the obvious thing to do is just take the straight line connecting this and this. That will do the job. So, well, now what would be the, so if I want to, this is for n equals 1, but it's easy to generalize it to any value of n just by, you want a, so for example, in R2, you would have a ball of radius epsilon by 2 and a ball of radius epsilon by 4 centered at x, epsilon by 4, epsilon by 2. So you want a function phi of x, phi of y. So y is the coordinate here. Now all one does is you have the option of making this function a one variable function just by taking the norm. So I'll make it a what is called a radially symmetric function. So the function is the value of the function at any point just depends on its distance. So it's the same on this all this concentric circle. On this circle, it assumes a single value. That's what this is doing, this part. But if you're just going to look at norms, then one can just use whatever the picture that we have here. So what I do is let phi of y equal to epsilon, the larger radius, epsilon by 2 minus norm x. First of all, of course, I declare it to be 1 if y belongs to bx epsilon by 4, and I declare it to be 0 if y norm y minus x is greater than or equal to epsilon by 2. And in the transition region, I just use a straight line which in the following way, and phi of y equals epsilon by 2 minus norm x, not norm x, norm y minus x divided by epsilon by 2 minus just epsilon by 4. Norm y minus x less than epsilon by 2 greater than or equal to epsilon by 4. And this formula I just got by looking at this, a straight line which goes from, tapers from 1 to 0. So notice that, of course, this is a piecewise defined function. So outside this ball, it has a certain form. Inside the smaller ball, it has a certain form, and on this annulus, it has some form. So to see that this is a continuous function on Rn, you just have to check at where these open sets, where they all intersect. This is an open set. I mean, the closures of these open sets intersect. So in the transition region, so I just have to check what happens along this, the boundary of the smaller ball, boundary of the larger ball. On the boundary of the larger ball, well, norm y minus x is epsilon by 2. So I'll get 0. On the boundary of the smaller ball, norm y minus x is epsilon by 4. And if I subtract and divide, I'll get 1, which agrees with what happens on the inside. So things are fine. So this is continuous. So I do it for all these points. I just showed you the general thing. Here we have these points x1, x2, xs. So I do it for all of them, and I get phi 1 up to phi s, satisfying whatever we want. Now, as I had mentioned in the lecture, this partition of unity, that theorem holds, it's true even if we demand that the functions that we get are not just continuous but actually infinitely differentiable. In other words, partial derivatives of all orders exist. And if one wants such a stronger statement, then obviously this phi that I constructed here, well, this in any case, this is not the final F1, F2, Fs one is looking for, or rather C1, C2 one is looking for. But this will be used. But if one wants differentiability, then this picture will not work, because this lack of, at these points, this derivative of phi does not exist. There it's a bit more work is involved. But now in the continuous case this will do. So let's define so these are not this phi1, phi2, phi(s) are not the ones which will do the job. So let's take, let Ci plus 1 I'll define this 1 minus phi1, 1 minus phi, and then phi I plus 1. Where I runs from 1 to s minus 1. Actually, I think I would need I to run from 1 to s minus 1 is not good enough. So I would want C1 as well, right? So I would need it to so let us see this quickly. So C1, yeah. So C1 you define to be just phi1, and the others C2 onwards you use this formula here. Well, Ci will be, see, each of these phi's are less than or equal to 1, and they're all non-negative. So this will also be, this will lie between 0 and 1 as well. And what about its support? Support of Ci plus 1, support of Ci, or let's just take support of Ci plus 1 is contained in support of this thing, phi plus 1, because if this is 0, then this is also 0. So contained in support of phi plus 1. And of course, this will be in the way we constructed this phi. This will be inside some V alpha for some alpha. Actually, the support of phi plus 1 is exactly the smaller ball. This is that B epsilon by 4 xi plus 1. And that is by definition contained in some V alpha. Now, why we define this Ci in this way is that we want that sum to be 1. So let's add these up. C1 plus Ci plus 1 is, well, phi 1 plus the next term will be I equals 1. So that is 1 minus phi 1, phi 2 plus the, oh, not I here, it's S, plus right, 1 minus phi 1 all the way up to 1 minus phi S minus 1 and then phi S. Right. So the claim is that this is equal to 1 minus, well, yeah, I mean the claim is this is equal to 1 actually, but how do we see that? You can actually you can just, let's see, how does one, this is equal to 1 on K. It's not true everywhere. Because the point is that when when X is in K, yeah, okay, so let me do it. Actually, the way it is done is you don't directly simplify this, but rather you prove the inductive step like this. So you claim C1 plus Ci is equal to 1 minus phi 1, 1 minus phi for I between 1 and S minus 1. Well, true for I equals 1 in a trivial way, because when I equals 1, I just get 1 minus phi 1, which is phi 1. I mean, that's true simply because we defined C1 to be phi 1. Suppose it's true for some I, I less than, yeah, well, I already said I between S minus 1, true for I less than or equal to S minus 1. Then if you want to check the next one, you just add then Ci plus Ci plus 1 is 1 minus phi 1, 1 minus phi I. That's just this contribution here. Then Ci plus 1 by definition is 1 minus phi 1, 1 minus phi I. And then you also have phi I plus 1. So you just take out this 1 minus phi 1 common and you will get 1 minus phi 1, 1 minus phi I, and then finally you are left with Right, where was I? So, yeah, 1 phi I plus 1. Oh, but I'm getting a. Let's see. So, if I take this out common, I'll get phi I plus 1 minus 1. Yeah, that's okay. So, so I have this. What I want is, remember that this is what one wants. So when I add up all the way up to Ci plus 1, I should get 1 minus whole bunch of stuff. There's somewhere I made a mistake, I think. Let's see. So this is correct. The inductive hypothesis is this. And then Ci plus 1 is also correct. 1 minus V1, 1 minus Ci into Ci plus 1. Then, oh, yeah, that's okay. I mean, there's no mistake. So it's just that this does not anyway figure at all in the factorization. It is just this minus, I just combine these two. And here I'll write it as 1 minus Vi plus 1. So, which is exactly what we wanted. So, the analog of this inductive hypothesis for I plus 1. So, this is equal to this. Therefore, so now you go all the way, so we can go do this all the way up to I equal to S minus 1. So finally what I end up with is C1x plus CSX is 1 minus V1x 1 minus phi sx, and we are done, because and this is true for all x, of course. This is true for all x in Rn. If x is in K, then x belongs to Bxi for some I. This is, remember that this was what we had, our smaller ball, B epsilon by 4 xi for some I. But inside the smaller ball, we know that these phis, phi1, phi2, etc., the corresponding phi will be 1, which implies phi I x equal to 1 for exactly that index I. The other ones we have no idea. I mean, you must always keep in mind that how these balls, their balls may intersect. Even the smaller balls may intersect, and the intersection pattern may be very complicated. So we really can't say anything about what the other values are, but we know for sure that phi x is 1. That's good enough to say that this term just becomes 0 when x is in K. So this is a very clever way of ensuring that this is 1 for all x in K. So in fact, the part of the proof which requires some or a nice idea is this. Having obtained these phi's, how do we ensure that you'll get a bunch of functions with sum 1 on exactly on k. So that is the part which requires a bit of thought, and that's how one comes up with this. This is not the only way to do it. There are other ways as well, but this is one nice way of getting hold of these functions which add up to 1 on k. And we still have the properties that we want, that these functions are between 0 and 1 and the supports are in V alpha. So that completes the proof of, as I said, yeah, in this, when you see this partition of unity later on, broadly speaking, even for smooth functions, smooth partition of unity, one proceeds more or less like this, except that this phi's will have to be constructed differently, and also once having obtained the phi's, to ensure that you get a bunch of functions which add up to 1, what rooting does will work definitely, but there are other ways of, as I said, there are other ways of obtaining these CIs which will still add up to 1. Okay, so that completes this brief lecture.